actually this iron protoporphyrin compound. This porphyrin compound is actually not a protein. Okay, so this is called a non-polypeptide, not a protein. And that's called a prosthetic group. Okay, so a prosthetic group is this tightly bound, specific non-polypeptide unit which is needed for the biological activity. So a protein without its characteristic prosthetic group is called an aproprotein. And then if you go back a few slides and take a look at this one again. Okay, so note that here's the iron in myoglobin, or well, you can also look at this as the iron in hemoglobin. So note that these nitrogens here form that prosthetic group, that heme. Okay, so it turns out that this is actually this big ring compound. I didn't put in all the atoms in this compound. Okay, so in other words, with iron here, you have these 4 nitrogens coordinate, covalent bond to the iron, and this is this prosthetic group, which is not the protein part. This nitrogen here is bonded to the rest of the protein. Okay, and then for the 6th bond to the iron, you can either have water or oxygen, or well, you don't want carbon dioxide bond. Iron hemoglobin. Okay, so what's a coenzyme then?
So they'll bond to an enzyme to help it perform its function.
And can you give me an example of a coenzyme?
Like a metal.
Yeah, so 2 types. One are metals, one are organic compounds. So the organic coenzyme is also called a vitamin. Okay, so that's what these vitamins are called. The coenzymes are actually needed for the protein to behave and do its function. Without those vitamins, it doesn't work the way it's supposed to work. Then for hemoglobin, the last thing, the charge on the iron is iron 2+. So if the charge is iron 3+, the hemoglobin actually will not bind to O2. Okay, so that's the last slide. And there's some chemistry trivial information for you between now and whenever you forget these last few slides for this semester. Okay, so there actually will not be any questions on coordination compounds on the final exam. So if you decide you want to take some more chemistry, coordination chemistry is actually a pretty interesting topic. Okay, so really the only thing we have left to talk about is your final exam. So, do you have any questions on the final exam other than the question, what's going to be on the final exam? I already answered that question.
How many questions do you have?
Same as the rate.
Yeah, so for the take-home portion, there's 5 questions. You can do questions 1 through 4 with other students. If you do that, you turn in as group questions. 5 you have to do on your own. For the in-class portion, it'll be 3 pages long. These are the same length as a midterm exam. The focus of the final exam will be mainly on the topics we covered since the second midterm. Okay, so although the final exam is comprehensive, it'll be mostly on what we covered since the second midterm. So maybe one thing we could do is talk about some of the topics we covered earlier. So let's see, way at the beginning of the semester we talked about bonding and structure. And then we related this to organic chemistry. Now we know that organic compounds are classified by functional groups. And then after we did this, which was a review of bonding and structure, we looked at solutions in the solution process. So in lab, you did this by figuring out ways to make a strong cup of coffee, and also you applied that information by trying to figure out a way to decaffeinate coffee. Then we looked at some solution properties. Those were those colligative properties. So using those colligative properties, you can figure out a way, for example, to increase the boiling point of a liquid. So how would you do that? Yeah, salt. Do you have anything else besides salt? So only salt will work? What if your solvent isn't soluble? What if salt isn't soluble in your solvent? Yeah, so in other words, as long as you use a solute which is soluble in your solvent, it doesn't have to be salt. For example, the antifreeze in your car is ethylene glycol. Would you want to put salt in your cooling system in your car? I hope not. You don't want to do that, just to increase the boiling point of your ethylene glycol. Anyway, when we look at colligative properties, what was boiling point elevation? What was the other colligative property we looked at? Yeah, freezing point depression, and then osmotic pressure, and then was there one more? Yeah, that was vapor pressure lowering, which is the special case of the boiling point elevation. So when we look at colligative properties, that property is proportional to the yes, remember from the formula, for example, with boiling point elevation, we have delta TB. That's equal to I times KB times M. So each colligative property is directly proportional to well, not necessarily the number of particles. M isn't mass. Yeah, so note that it's proportional to the concentration. So the higher the concentration, the larger the boiling point elevation or freezing point depression or the osmotic pressure or so on. Then we also looked at, for example, let's see, in lab we also looked at things with sodas. Let's see, what did we do with soda in lab? We looked at the solubility of solutes and liquids. We looked at that too. And let's see, after that we looked at, let's see, from solutions. The next part was reaction rates. So what were the three factors which determines the rate of reaction? Yeah, so the three factors are, let's see, concentration, catalyst, and temperature. And then we can write a rate law for a reaction. So we look at a rate law. Remember, if we have some reaction, say A plus B going to product, we can describe the rate law by saying that the rate is equal to K, which represents the rate constant times the concentration of A to the X power, and then B to the Y power, where X and Y represents the so X and Y we call, there's a specific name for this, that's called the order. And then in lab you actually figured out a way to determine the order of the reaction. Okay, so in other words, you can do, one way to do is by doing different experiments. So if you double, for example, the concentration A and keeping the concentration B the same, what happens to the rate? So depending on what happens to the rate, you can figure out the order of the reaction. So for reaction order, it has to be either 0, 1, or 2. It's got to be a whole number. It can't be a decimal or fraction. Then from here, we can also look at reaction mechanisms. So based on the rate law, we can figure out the reaction mechanism. And what is the important step in the reaction mechanism? Because that step determines the rate of the reaction. Yeah, that's the rate determining step. Is the rate determining step the fastest step? Rate determining step. Is that the fastest step in a reaction mechanism?
It matches the rate.
Yeah, so the rate determining step matches the rate law, but is this the fastest step or the slowest one? So the rate determining, this is actually the slowest step because that determines the overall rate of the reaction. Okay, so from after reaction rates, we looked at equilibrium. Okay, so for equilibrium, now another term for an equilibrium reaction is a yeah, because see, in Chem 1A up to here, we said that reactions only go in one direction. But an equilibrium reaction goes in the forward direction and in the reverse direction, so equilibrium reactions are also called reversible reactions. And how can we quantify an equilibrium reaction? Yeah, by looking at the equilibrium constant KEQ. So rather than KEQ, this is the concentration of product divided by reactants. Okay, so once you have your balanced chemical equation, this has to be raised to the power of that coefficient in your balanced chemical equation. And then you can make a reaction go in one direction or the other direction by applying some principle or some law. And what was that? What was that principle or law? Yeah, Le Chatelier's principle. Okay, then we apply these equilibrium principles to acids and bases. So the acids basically look at Ka and Kb. And then from here we also looked at we looked at titration curves. So with titration curves we also looked at buffers. And then going back to, actually before we go on, when you look at Le Chatelier's principle, we said that are most reactions endothermic or exothermic? Yeah, most reactions are exothermic, so if we increase the temperature for a reaction, two things can happen. If we look at reaction rate, increasing the temperature is going to do what? Yeah, so increasing the temperature is going to they make the reaction go faster, but if you have an exothermic reaction in which heat is a product, because you have A plus B going to C plus heat, if you increase the temperature, what happens to the direction of the equilibrium reaction? It shifts toward the reactant side. So by increasing the temperature for a exothermic reaction, is that going to improve the percent yield of the product? So if you wanted to increase the rate of reaction and also increase your percent yield, rather than increasing the temperature, what did you do? You use a catalyst. Find a catalyst to use. Okay, so then from here, we looked at thermodynamics. In which we quantified energy in chemical reactions or physical processes. So we looked at several different quantities. We looked at work and heat and internal energy and enthalpy and free energy and entropy. We looked at all those quantities. Now, what are the two driving forces for a reaction? Okay, so the two driving forces are entropy. Okay, entropy is one. What's the other one?